generation and recombination, we might, and continuity equation. I don't know how far we can go with today's lecture, but we can have the whole topics on this page be divided into 2 lectures today and on next Tuesday. So let's start then with the diffusion current. What do we mean before we start with diffusion? The word diffusion, it means that you have particles that will diffuse from one region to another, from higher concentration into a lower concentration by means of thermal motion, meaning changing the temperature will cause the particles to move from a higher concentration into a lower concentration. Okay, so here I have done for you the derivation for the diffusion current like we did with the drift current. As you know, for any semiconductor material, what you have the total current will be the sum of the drift current plus diffusion current plus generation recombination current. So we already derived the drift current, which due to an electric field. Now we want to derive the diffusion current, which is due to transport of carriers. So what we will do is I will show you what do we mean by the electron flux and how it moves from a region of L across to R, or R across to L, which should be about half. So then we can obtain the concentration carrier. So let me show you the drawing, then we will go back to the derivation. So this is what we mean. I have drawn for you, if we are talking about a concentration as a function of distance, you know, like if I'm traveling or the particles are crossing a length, we call it the mean free path L, from one region to another region in a time t. The mean time, we call it the scattering time. So in this case, what we are talking about, we're talking about that the region from across from x0 to x0 plus 1, which is going from L to R, should be the same amount as going from x0 to x minus 1 from R to L. So let's then go back to the derivation. In the derivation, we're saying that hence, if we are saying that L to R crossing across x to x0 is half, and similarly, if we're going from R to L, which is from x0 to x, and that implies that we're going a concentration of NL in one region and minus N sub R in the other region, since it's on the negative side of x0, over 2. So we're summing and taking the average of the two. So the concentration delta N, then it's in a time dx will be, so NL plus minus N sub R over 2. Hence the flux, which is a unit of per cross-sectional area. So we're talking about per centimeter square second, and the concentration here, it's per cubic centimeter. So it's times the free path we talked about, the mean free path, over the time that it took for these concentration to move, and the 2 is from summing here. So this is the delta NL over tau scattering, okay? Where, of course, we're talking about NL minus N sub R is the total, which is minus dN by dx times the mean free path L. So if we rewrite our flux phi of sub n, so here we're talking about electrons, and it will be the same for holes. So phi sub n of xt, then it's minus L square, the mean free path square, over 2 tau scattering dn of x by t by dx, and which is equal to minus dn of x of t dx. So this parameter here is called the diffusion coefficient, and it's diffusion constant for every material. So it will be given for every material, which is equal to L square over 2 tau scattering, or we say actually the mean free path for material that has a concentration crossing over in a time t, equal then to the square root of dn tau, which is then if we take the square root of L. So, but the current, the diffusion current is defined as minus E phi sub n. So since there is minus here and minus here, the minus is for the electrons, the charge, so it is then equal to plus E dn of x by dx. In here, I said, okay, in that case, if I'm talking about the total diffusion current, meaning that I'm including the holes and the electrons in a semiconductor material, so then it is E dn of x t by dx minus E dp dpx t by dx. The minus here because, as you know, that the flux for holes has this negative sign, but the charge is positive, so then the minus sign will stay into the equation. Any question? Is it clear how we... Yes.
ليش أخذنا ال NR نيجاتيف حطينا minus NR؟
لأنه لا أحط لك بتشوفي ساعتها أوكي الآر وين؟ عم نقول الان ار، يعني أنا عندي هون ان ار concentration in the R region. إذا بدها تنتقل على ال راحت من higher to a lower، أوكي، فصارت minus NR، عم تمشي بعكس الاتجاه تاع الإكس.
ال والR هن الريجنز، يعني أسماء الريجنز.
إيه أنا حطيت الريجن from L to R or from R to L. إذا ماشي from L to R يعني أنا عندي هون كلها concentration of electrons. ما يعني كأنك عم تطلعي أنت بالبي ان دايود، بس خلينا نقول بس عندي N material. إذا عندي N material عندها electron, excess of electrons. excess of electrons, they might move from a higher region to a lower region. اوكي، بس نحن عم نقول قديش في عندي، افترضي انا عندي هون ال N sub L انتقلوا من هيدي الريجن لهالريجن، يعني وحطيت كأنه انا هون اخذت part of NL، يعني اخذت part of this region وسميته بس كأني عندي هون هالريجن هي L، وهون عندي الR كلها R وأخذت هالريجن من الR. عم بقول إذا انتقل لعندي إلكترونات من ال على الR يعني across x0 معناتها راحوا in the direction of x، يعني in the positive direction، معناتها n sub L R positive. وعندي عم بقول الاحتمال probability is the same. ليش؟ لأنه بده يكون في عندي equilibrium هون. لما بده يصير في عندي equilibrium يعني قد ايه انتقل كمان NR من الR على ال about the same. عشان هيك جمعت هالconcentration أنا قلت ال N sub L plus ال N of R هي نيجاتيف اللي قعدوا هون لأنه راحوا بعكس الإكس دايركشن، بس الدايركشن عم تعطيني النيجاتيف. So the delta N is the summation or the summation of the two concentration in the two region. وضحت؟
دكتور thank you.
You're welcome. Okay, now we're talking about diffusion current. So I'm just showing you the concentration of N as a function of X. Since I show you that we have a minus sign for the drift current due to holes, due to the flow of holes. لأن الholes will current, they flow in the same direction, so they have a negative with respect to the charge, while the electron flow would be in the opposite direction of the current flow, and that's why negative with negative give me a positive charge here on the current. Okay, now in here, we're going back into the drift current and the diffusion current. We're saying that the total current is the sum of the currents due to holes and due to electrons, or Jn plus Jp, electrons plus holes. So Jn, which is so far we have contributed to the drift plus the diffusion only. So we added the drift current, which is En mu n times the electric field, plus diffusion that we just derived, it's E dn by dx. And the current due to holes, again, is the drift plus diffusion, so it's E p mu p times the electric field minus E dp dp by dx. Okay, before we go on another slide, in here we have total current due to electrons, total current due to holes, without including the recombination generation current. We're saying at this point, we said that most of the current, or the total current, since the generation recombination current will be very little, and in most cases we not consider it, but we're going to do the derivation for it and talk about it. If time's allowed today, we do it today. If not, the next lecture. But today what we want to do is to deduce from these two relations under thermal equilibrium. We're going to say that either if we're talking about electrons or about holes, the Einstein relation will end up the same. We will have a relation which will relate the mobility of the electron with the diffusion of the electron to the kBt over E. And the same thing for holes. It will be the same relationship. So in that case, we will reach to an equation which will relate dn mu n to dp mu p if we're talking about the same system. Okay, Einstein relation, we said in equilibrium, there is no net flow of current of electrons or holes. Why? Because we don't have an external applied potential. We're talking about only the built-in electric field that exists, which you will see it after when we reach to the PN diode in the coming few lectures. We will be talking about how we will obtain, or how did we obtain that. If we're talking about, for example, silicon, we said it's 0.7 volt, that's the built-in potential. So with the built-in potential, that means I didn't apply an external applied potential to the system. So in that case, we say that the net current due to electrons will be zero, and the net current due to the holes will be zero. So we assign this equation So in case you're asked to derive Einstein relation, and I will say under equilibrium, the net flow of currents and holes is 0, then you know that this equation is equal to 0 and this equation equal to 0. So in that case, the next one will be, you will reach to that equation. And here I just put it as an example. I said we have reached to kBt over E equal to dP over mu n. So before we go to the example, if I look back at this equation, I set Jp equal to 0. So that implies the E, the charge is out of the equation. So I have P mu P E equal to dP by dx. So now I have to relate the electric field to this, to write the concentration P to dP by dx, what does it equal to, and then relate the electric field to the equation that we had before. Okay, so what I want to show you then, I will be coming back to that equation. Look at here. If I'm talking about P, then P will equal to NV e to the E F minus EV over kBt, and then I will write dP by dx, then will come to that equation, which becomes minus n ala kBt dEc by dx, which is equal to this equation. Okay, so if I'm going back now to the equation of Einstein, I had at first to start with taking dN by dx or dP by dx. If I'm telling you I have a p-type material, then I will write dP by dx will reach to, without the minus sign, it will be P over kBt E times the electric field. Then I will substitute back into the equations, which will reach to that equation, the previous one in here. Okay, so now I have a relationship between P and dP by dx and the electric field, E times the electric field. So I substitute, I will obtain kBt over the charge equal to dP over mu p, and the same thing, since for n I have minus, so the minus on this side will be get rid of, and I will obtain the same equation. If I'm talking about P or N, Einstein will give me kBt over E will equal to dP over mu p equal to dN over mu n. So as well, kBt over E is known, since we know that at room temperature it's equal to 26 millivolt. So and the diffusion and the mobility, usually the mobility of electrons or of holes will be given for every material, so you can determine the diffusion constant from the equation. So it's a constant in a way. If it's not given, unless I change the temperature, then you have to take into account this equation and substitute for the change of temperature. Now here, which should have been before doing the Einstein relation, we're talking about the equilibrium of the Fermi level, which usually it's constant for if there is if we're talking about uniformly doped material, meaning that if I'm talking about, let's say, N-type material and it's a pure and it's no uniformly, like when I dope my doping substance into silicon and the surface is uniform, the Fermi level will be constant. Now, of course, the energy gap for the, the energy level of the conduction band or of the valence band, depending on the relative between, if I'm talking about N or P, if EF will be close to EV or to EC, depending on the type of the particle that we are putting into. Okay, here we said about N-type, then this change dN by dx, we obtain it using that equation. As you notice, it becomes EC that is changing, not EF, since EF is uniform, and in here we are talking about the built-in electric field. Okay, that's another equation that we went through in a way, if we're talking about the neutrality equation, which we noticed it in the example we did before. But in here, we're going to write it down and say what we mean by writing this neutrality approximation. We're saying that if I have a material, then the density of the doping material plus, due to the donor atom, so the donor density plus the holes equal to the acceptor plus the electron. Since we know that roughly the density of the donor will be equal to the concentration of the electrons, and the density of the acceptor will be roughly equal to the density of the, or the concentration of holes. So if we're talking only about N-type material, in N-type material, roughly I don't even include the N acceptor unless in the question you're given and you're asked to determine the concentration of electrons, then I have to just subtract the concentration of the acceptor from the density of the donor. The same thing apply if I'm talking about the concentration of holes. It will be roughly the concentration of the acceptor. But then in that case, again, it will be Na minus Nd. And in P-type material, we already written that equation from the previous, we obtained that electric field equal to minus kBt over E 1 over N dN by dx. And it can be written as you notice that it's Nd. So N, the concentration of electrons, can be substituted by the density of the donor. It's roughly the same. Okay, so now that we have talked about everything concerning the diffusion current and how can we obtain the neutrality equation, we come to the next topic, which is generation and recombination. If I'm going too fast, please stop me and say, are you okay with the slides and with the lecture, or am I going too fast?
Yes, doctor, it's okay.
So you're okay. So now we will be talking about what we mean by generation and recombination. Okay, I might, like in few slides from here, I will stop and leave the next lecture to the rest of the of this PowerPoint slides. Generation, we mean by generation, process of electrons and holes pair. Like we create by having electron and hole pairs will be created. How this will be done? only by generation, meaning without, if an electron went from a conduction band into a valence band, occupying a vacancy, then we said that electron hole are created. And the same thing apply. If an electron from a valence band went up to the conduction band where it found a vacancy and sat on that, it created electron hole pair. So that's what we say by generation. Now, recombination, it's an annihilated in pairs of electrons and holes. We have two processes of recombination. We can talk about radiative and non-radiative recombination. We'll see what's the difference between radiative and non-radiative recombination. And we'll see how the processes are done. Then we can reach to the equation, or the after doing, I mean, in this lecture, we'll only reach to the continuity equation, and we'll leave the derivation for the generation recombination current for another lecture as well. So I might add the generation recombination current in the next slide, and we'll see how we will obtain the I due to generation recombination. Now, in the generation process, as I said, due to thermal energy or light, you know, if you impinge a light on a semiconductor, it's like the we say the light emitting devices. Then an electron that was sitting here, it left the valence band and found a vacancy in the conduction band and sat on this position. Okay. Of course, if we want to do recombination, what it happens is that at first they did a level here, we call it, they formed the pair, the electron hole pair, because it might not be able to jump all the way to the conduction band. So at first they recombine, form a pair, then got emitted up or absorbed. We say absorbed up to the conduction band. Emission will be down, absorption will be up. Okay, so here we're talking about recombination, the same thing without that step, directly, and a light being impinged, so it got an electron that was in the conduction band, got absorbed back into the valence band, and so on. So as you see, then we can form within the same material recombination generation pair or current. So now what I want to go through is the radiative recombination. So I did the radiative recombination for you, so you will know what type of spontaneous emission we're talking about, how we relate it to the time that it takes, to the tau time or relaxation time, we call it, and how we relate the gain that got through the material from emission absorption, and how we relate it to the intensity of light through the material. So we will go step by step. We're talking about, we said, radiative recombination. Radiative recombination, what does it mean? We said when photons impinge upon a semiconductor, it can be absorbed by moving an electron from the valence band to the conduction band. The photon beams decay as it moves through the semiconductor. So the process of absorption requires that the valence band state to have an electron present and the conduction band state to have no electrons. So in that case, what it means, so that the electron, when we impinge a photon, we impinge that light on the semiconductor, it causes that electron that's sitting in the valence band to be absorbed into the conduction band. So it went from valence up to the conduction band. We said that the electrons in the conduction band is being absorbed from the valence band. If electrons are found in the conduction band and holes in the valence band, then we say that this through electron hole pair recombine, that means it has emitted a more photon and can be absorbed again. So what happens if an electron loses some of its energy and then it gets emitted back into the valence band? In the valence band, they will create a electron hole pair without the need of an additional photon to be from the external. They can recombine with each other and then they will emit again an electron from the valence to the conduction, so the conduction will absorb that, and this is what we call light emitting devices. Hence we say that this gain is proportional to what we call the density of the conduction valence. So it's the combined density of the two. So it's the recombined electron and hole. So when we talk about density, we're talking about the density of the state density due to electron hole pair. So due to electron hole pair, we call it CV, and we said that this gain is proportional to this density. And we say that the intensity then is given by this relation, which is equal to I0 exponential of the G times the height. So we're talking about intensity of light passing through a direction Z have an initial intensity. So this is the intensity through the material equal to the initial intensity of the light crossing into the material times the exponential term, which is the gain due to the electron hole inside the material times the height or the direction we're going. Now we said for photons emission process to occur, no need for photons to be present. This can occur due to the electron and hole being pumped into semiconductor, where they recombine through the process of spontaneous emission. So now we said, what do we mean by spontaneous emission? It's the rate per unit volume, which is proportional to 1 over the relaxation time. Okay. Here we said there are different cases of spontaneous rate depending on electron hole injection. So we want to see what type of material we're talking about and how does this rate correspond to. If we're saying that N much greater than P, so in that case we're talking about N-type material. For N-type material, the spontaneous rate will depend on minority carrier. Minority will be the P, since majority is N. So in that case, it will be roughly equal to 1 over the relaxation time. The combined mass, R for recombination mass, the effective, of course, because it's inside the material and it will be related to the free mass, over the whole material, the whole mass, which is the minority material, times the minority concentration. So this is the equation we're saying. So the other day, one of you asked me if there will be a question, multiple choice questions or true, multiple choice. And I said all what I can ask. Let's say I ask you to describe radiative recombination. Okay, so you can go through all the steps from the previous slide to this slide, explaining all the 4 types of spontaneous emission, and we talk about the response to it. So in that case, we said that if I have a majority of N and minority of P, then this what would be. So I will, of course, specify for you what type of material we have, if I'm talking about N or P, and then you can, of course, let's say I'm talking here about P being much greater than N, then the minority will be N, then the spontaneous response will be 1 over tau due to N, of course. MR, the recombination, the effective recombination mass, over the effective mass of the electron to the 3½ times the N, the concentration of electron. Most time we use the spontaneous when N and P are in the material and both are of about the same. In this case, it's equal just to N over tau and P over tau, so it will be the same. If I'm talking about a weak injection, then in that case you have to use Boltzmann approximation. Hardly we use U, and it will be the spontaneous proportional to MP. So in this course, I'm not going through the derivation of every one because you will not be responsible to derive. And for inversion condition, which we will see the inversion when we reach to the MOSFET material. At the point we just talk about the inversion being the due to the distribution function for electron plus the distribution function of holes equal to 1, which will give me that the spontaneous rate will be equal to N over 4 tau and roughly P over 4 tau. Any question?
دكتور بس شو هي الانفيرجن؟
Which inversion? Inversion condition. We'll reach to that, but I will tell you what we mean by inversion. Inversion meaning that you think you have a P-type, okay, and by injection it will flip and become an N-type. So that's what we mean by inversion condition. Depending on the injection of particles or of particles from other material, okay? So if I inject by at some time, it will reach to as if I'm seeing an N-type rather than P-type. Let's say I have a P-type, okay, and I start injecting the P-type with an excess electrons to a certain level, the Fermi level will change and it will become as if I'm seeing an N-type material. So in that case, we said inversion condition, and that's why the spontaneous rate is divided by 4, is equal, and they are about the same, N over 4 tau and P over 4 tau, while when they were both injected, I was injecting the material, the silicon material with N and P. In that case, I had it equal, the spontaneous rate was about the same, just concentration per unit time and concentration per unit time. Did it clear it?
Yes.
Okay. So in here, all what I'm going to do is talk about the non-radiative effect. Let me see what's the next slide, and then I will go back. Okay, I will leave that till next lecture. So I will give you this slide and we'll stop recording, but I will send you the full file today with the recording session, and then we will continue this lecture on Tuesday since the continuity equation will take time, and I will do the derivation for you as well and include it because it's not included in for the recombination generation current. Okay, for non-radiative effect then, all what I'm saying that in real semiconductor there are always intentional or unintentional impurities. What do we mean by that? Simply we say silicon is a pure material. So I will let's say inject an N-type, and I make an N-type, and I inject a P-type, and I make a P-type in the same material I had PN semiconductor to form a diode. What we said that the energy gap between the conduction band and the valence band should not have any electron sitting at any state. So either it will reach, it will have enough energy to jump from the valence band, from the top band of valence to the lowest band in the conduction band. So this we say that the semiconductor are a pure semiconductor. Now, if impurities occur, sometimes you need to have electrons sitting in the energy gap, or sometimes it's impurities happen and you find electrons in the band gap. So that's what we call a non-radiative effect will happen. So this is sometimes desirable, we say. So initially we put electrons in the energy gap. So in that case, what causes the PN diode to be, we want to increase its speed, like we will see in Schottky diode. Schottky diode, actually we can put metal, for example, on the PN diode, and then in that case we will form a Schottky diode which will increase the current, because we know in metal we don't have energy gap, so it's all the electron and holes, they overlap, so the current will be much faster. So we can say that we have created a trap density in the energy gap with a cross section, call it sigma n, and a thermal velocity V thermal. So that we call an intentional. We said if we want to speed the current in the PN diode, we create an area in the band gap where we have trapped some electrons in that region at a certain thermal velocity and within a cross section. And we will relate this tau. Of course, you reach to that equation, not simply like that, but you reach to that equation by a whole derivation for the trap density and the thermal velocity and the cross section. But in here, we're just saying that tau n equal to 1 over nt V thermal times the cross section n, and the tau p is equal to 1 over the trap density, thermal velocity, and the cross section of the hole. So that's, in that case, that's the difference between tau n and tau p. It's the cross section n and the cross section p. And we say that the rate, we know that the rate is dN by dt, as we saw from previous slide. For n, it's negative because we're talking about electrons, and for holes, it's dP by dt. And if we're saying that tau n and tau p are equal, then we said that the rate can be defined for the recombined Like if I'm talking about a PN diode, that means I have N and P. And if I say N and P, the relaxation time or the time it took for the electron and hole to be trapped is the same time, then I can refer to it as a NR. And then in that case, the recombined rate is equal to NP over tau NR into N plus P. So for that, we know from this rate, we were able to obtain the non-radiative effect in a semiconductor. Any question before we stop recording? I guess no one is present, maybe.
لا موجودين دكتورة.
لا.
موجودين. But because you're so quiet, I see only 10 students are attending. Okay, according to the registration, there is 42 students in my class. I guess no one is taking the other class.